Okay, 10.11, Taylor polynomial approximations. So it says Taylor polynomials are created to help us approximate other functions. It says, why would we do this? Well, because polynomials are easier to work with when we're taking derivative and integration. A Maclaurin polynomial is a special type of Taylor polynomial. It says, to start, we choose an x value to center our polynomial approximation. We are going to call this center x equals c. Our approximation will have the same y value as the original function at x equals c. So this would be us saying, okay, on our graph off to the side, some value here is c, and then that same value corresponding with the function is f of c. It says we expand the approximation about x equals c. Another way of saying this is that the functions are centered at x equals c. So that value that I placed for c on the graph is where all our functions that are going to approximate this function is going to be centered at. So we write that as f of c is equal to p of c, where p of c is our approximation. It says explore with an example. So we have f of x is equal to e to the x power, let c equal 0. Okay, so that means we have f of 0 is equal to, well, e to the 0 is 1. Okay, so we have f of 0 is equal to 1, which implies that p of 0 is also equal to 1, since f of c is equal to p of c. Okay. So it says we want to make the graphs have a similar shape at the point x equals c. This means that they should have the same slope. Well, anytime we mention slope, we know we're talking about the derivative. And so that means f prime of c is going to be equal to p prime of c. They have to have the same slope. So in our example, that means f prime of 0 has to equal p prime of 0. Well, let's go ahead and use a polynomial approximation. And in order to do this, we're going to first set up this approximation that's going to look like the point slope formula. So that y minus y1 equals mx minus x1. And so setting that up, we have the equation that looks like p of x minus f of c is equal to f prime of c times x minus c. We can rewrite this by moving f of c to the other side. So we have p of x is equal to f of c plus f prime of c times x minus c. And then using our example where we know that c is 0, I'm going to plug in 0 for c. So I have p of x is equal to f of 0 plus f prime of 0, okay, times x minus 0. And we know f of 0 is 1, and we also know that f prime of e to the x is e to the x, so that means f prime of 0 is also going to be 1. So we have 1 plus 1 times x, which is equal to 1 plus x. This equation here is going to be called a first order approximation. Okay, because we only use the first derivative to find this approximation. So if I go over here and I plot my point 0, 1, okay, because c is equal to 0, and then I look at my approximation 1 plus x, I get the following line. I'm also going to color code it with my approximation. And so now I got an approximation for the function e to the x. However, if you look at this first order approximation, you'll notice this is not a great approximation for e to the x. It is representing the function as a line, which is not going to approach the same values as the actual function. So in order to improve this approximation, we're going to take the second derivative. Okay, so they already did this for us. It says We want f of c equal to p of c, which means the first derivatives are equal and then the second derivatives are equal. So in our example, since the second derivative of e to the x is still e to the x, that means when we plug in 0 for x, no matter which derivative we're taking, they're all going to be equal to each other. So if we go to a similar process, we're going to get a second order approximation of p of x is equal to 1 plus x plus 1/2 x squared. So if I go up and graph that, I'm going to get a quadratic that looks like the following. I'm going to color code it to match. And so notice my second approximation is getting a lot closer to the original function e to the x. So my second order approximation is already much better than my first order approximation. Well, we can continue this process and do the third derivative, the fourth derivative, the fifth derivative, etc., to get the best approximation possible. So let's look at what that would give us. So if we are centered at x equals 0 because c is equal to 0, it says then we have the following pattern. So p sub n of x is talking about the nth derivative. So we would have 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed all the way until we have this. 1 over n factorial times x to the n power. This is called an nth Taylor polynomial. So it says if f of x is differentiable, okay, which means we can take the derivative, then an approximation of f centered about x equals c can be modeled by the following equation. So we have f of c, and you're going to have to write pretty small here, plus f prime of c times x minus c, plus f double prime of c times x minus c squared over 2 factorial, plus f triple prime of c times x minus c cubed over 3 factorial, plus dot 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 all the way until f to the nth derivative of c times x minus c to the nth power all over n factorial. And so this n is the order of approximation. So then that leads us to what we talked about in the beginning, and that's the Maclaurin polynomial. Remember, the Maclaurin polynomial is a type of Taylor polynomial, and the only difference is that this has an exact center, and it's always going to be around x equals 0. And so this can be modeled by the following equation. So anywhere we see an x in our Taylor polynomial, that x is just going to go to 0. So we have f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial plus dot 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 f nth derivative of 0 x to the n power over n factorial. So let's look at some examples using the Maclaurin polynomial. So it says find the third degree of the Maclaurin polynomial when f of x is equal to e to the 2x. And so first I'm going to write my formula. So I want the third degree, so this is p sub 3 of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 x squared over 2 plus f triple prime of 0 x cubed over 3 factorial. And so now I just need to plug everything in. In order to do that, I need to find my first 3 derivatives. Well, f is equal to e to the 2x, so f prime is 2e to the 2x, f double prime is 4e to the 2x, and f triple prime is 8e to the 2x. And then if I plug in 0 for each one, f of 0 is 1, f prime of 0 is 2, f double prime of 0 is 4, and f triple prime of 0 equals 8. And so I plug in that and I get my approximation. So I have p sub 3 of x is equal to 1 plus 2x plus 4x squared over 2 plus 8x cubed over 3 prime, which reduces to 1 plus 2x plus 2x squared plus 4/3 x cubed. This would be my approximation to the function e to the power of 2x. Okay, now it says evaluate at f of 0.2 and p sub 3 of 0.2. So we're going to see how close our approximation is. And so for this, I would just plug this into the calculator. So f of 0.2, which means this is e to the power of 2 times 0.2, which is 1.4918. And then p sub 3 of 0.2 would be 1.4906. And so remember, this is our approximation. This is our actual value. So look how close we got with this approximation, which means this is a very good approximation for the following function. Okay, next example. It says find a 4th degree Taylor polynomial for f of x is equal to natural log of x centered at x equals 1. And so I'm going to write down my formula first. Okay, notice it is a Taylor polynomial where they gave me the x value. So this is p sub 4 of x is equal to f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 times x minus 1 squared over 2 plus f triple prime of 1 times x minus 1 cubed over 3 factorial. And it wants the 4th degree, so I have to add one more. So f 4th derivative of 1 times x minus 1 to the 4th power over 4 factorial. And so in order to solve these, I need to take and find the first 4 derivatives. So f is natural log of x, f prime is 1 over x, f double prime is negative 1 over x squared, f triple prime is 2 over x cubed, and then f to the 4th derivative is negative 6 over x to the 4th. And if we plug in 1 for each of these, f of 1 gives us 0, f prime of 1 gives us 1, f double prime of 1 gives us negative 1, f triple prime of 1 gives us 2, and then f to the 4th derivative of 1 gives us negative 6. Okay, yeah, just verifying everything. Okay, and so once we have that set up, that means we can write our answer. And I'm going to have to move into the next space because I'm running out of room. And so this gives me p sub 4 of x is equal to 0 plus 1 times x minus 1 plus negative 1 times x minus 1 squared over 2 plus 2 times x minus 1 cubed over 3 factorial plus negative 6 times x minus 1 to the 4th power divided by 4 factorial, which is x minus 1 minus 1/2 x minus 1 squared plus 1/3 times x minus 1 cubed minus 1/4 times x minus 1 to the 4th power. Okay, so this is what it would be simplified. So in this next part, it says evaluate f of 1.1 and p sub 4 of 1.1. So I'm just going to change the color not to get them confused. So f of 1.1 would be us plugging in 1.1 into the original function, which is natural log of x. So this is natural log of 1.1, and that gives us 0.095319798. And I'm showing you lots of decimal places because I want to see where our estimate got. So this was our actual. And now let's look at our estimation, our approximation. So p sub 4 of 1.1, This gives us 0.095308333. So notice, let me change the color here. We got all the way up to this many decimal places correct, which means that our approximation had a very small error. Okay, and that's good. That means our approximation was almost exactly our original function of natural log of x. So that leads us to the next part, which talks about the coefficient of a Taylor polynomial. So it says the coefficient of the nth degree term in a Taylor polynomial for a function f centered at x equals c can be written as f of the nth derivative of c over n factorial. So if we're looking at an example where it wants us to find the next degree, like number 3, we can easily find that using the following formula. So it says let f be a function with a third derivative of the following. What is the coefficient of x minus 2 to the fourth power in the fourth degree Taylor polynomial for f about x equals 2? So we need to find the fourth derivative of x. Okay. So what I'm going to do here is I'm just going to take the derivative of the third derivative given. So I get 3/2 times 8x plus 2 to the power of 1/2 times 8 using the power rule and the chain rule. And then I'm going to plug when x is equal to 2 using the following coefficient Taylor polynomial formula above. So I have f to the fourth derivative of 2 over n factorial, so that would be 4 factorial. And I'm just plugging everything in. So that's 12 times the square root of 18 over 4 factorial, which is 36 times the square root of 2 over 4 factorial, which simplifies to 3 square roots of 2 over 2. And that would be my answer.